Okay. I think we finished the last chapter. We need to solve more examples in general for anything. But I'll try to finish the material fast enough, and I will not lose any physics concepts to make a room at the end of the semester to solve more examples as a review for them. Okay. Now we talk about chapter 10, which is the dynamics of the rotation of motion. And the first section of this chapter is the torque. We know about the torque. You will see that we know what is the torque. Previously, when we apply any force on any mass, this force is a vector. The mass will accelerate in the direction of that force by Newton's second law, which is F is equal to ma. This motion is linear, but you remember that in the previous week we start the rotational motion. Now we will not deal anymore in our study, this chapter, with linear motion. We will talk always about rotational motion. Okay, for example, you know this tool. How we use it? In general, you know that we rotate it in this direction or in this direction. But if I ask you to apply the linear force on that tool in this direction, this is a force. It just simply will move to this direction without any rotation. It will keep its orientation, right? Because we just applied a linear force. We don't have any rotational effect for this force on this object. I will not put that screw here now. We don't need it. Also, this game, you know it also. If you need to remove or to move it from side to side, you will just push it by a force and you move it with the same direction for it, with the same orientation. It is just a linear force. Or if I let this object fall like this, you see it starts its motion like this. When it is moved under its weight effect, it keeps its orientation, right? Look at it again. If I give it any rotational effect, it will rotate, right? This is our study today. Any question about that? This is a previous material. We will apply it on things, materials can be rotated. And the main law in our study is Newton's second law. We'll start with this law. In general, it is the main formula in physics, this law. Okay. But we will see that this term has a meaning in our study. Okay, again, now if we have a rotated object, this object can be rotated. It is fixed at a point. This point is O, for example, and it is fixed here. If we apply any force, for example, if we apply this force, its effect is a rotation, right? If this force is equal to 5 newtons, and this is its direction. If I need to change the direction of this force by this way, it is the same magnitude, it's 5. Do you think the rotational effect is the same? Or if this force comes like this. Now, there is a direction between the force and the origin or the point of the rotation. Look, there is a change in the direction or the angle with respect to this point. What is the line that tell me there is a change in direction? It is simple. If I look to this, where is the point that the force acting on it? It is here. I will take one of these forces. Let me take this force. There is a line, straight line between the point of rotation, which is O, and the point that the force acts on it. This line from here to here, I can take it like this to make it more simple. This is X and this is Y. For example, you can see that this is a position vector direct to the place of the force. So the direction of this vector is to this direction. So I can name this vector by R. And this is the force. Now, if you look at R and at the force, there is an angle between them. If my force is this force, there is another angle because I have, this is the first angle and this is the second angle. So, because the change in angles, because I have different angles, then I have different rotation effect or rotational effect, okay? Now, we know from before that the force has a linear effect. But in this case, we fixed the object at this point, at one of its points. Then the object will rotate. So we have a rotational effect. This object will rotate in this direction. Is this direction? I need to ask you now, I'm asking, is it positive or negative direction of rotation? Positive. If we remember that from before, we told you that measurement of the angle is counterclockwise. So this direction is positive and this direction is negative. That's important in general. The directions in our study is important almost. Okay. Now, the rotational effect of this force at this point, which is R in distance, it is another force, but it is a rotational force. This rotational force has a new name in physics, in our physics. It is a torque. Okay? It is a torque. What is the torque? It is a force acting on a distance from a fixed point, and this force will rotate this object. Is this idea simple? Now, the torque has a sample tau. Any question? And always we have, as we know in physics, any quantity will be connected to other quantities with a formula. And the torque has a formula connected with the force, because the generator of the torque is the force, and the torque will be changed or depend on R. So in my equation, I must see R and F. F is a vector, and also R is a vector. And also I need the direction between them, this angle. This angle is theta between R and the force. I'll remind you by this formula. This is a mass, this is a force, and this mass will move to this direction. Distance x as a vector, this is force as a vector, and they have angle between them is theta. What if I take f dot x as vector? It will give me f x cosine theta. What is this quantity? Yes, it is right. It is the work. What is the units of the work? If you remember, it is joule, or it is equal also to the force has newtons and x has a meter units. So in our previous study, we studied that there is an interaction between a force and a distance, and the angle between them. There is a formula, cosine theta, fx cosine theta, and the units newtons meter are equal to joules, which is an energy, because it is energy. Yes. Now we have a distance. It is r. Be careful that x, the object move x, move this distance, but the object will not move this distance r. The object length is r. It is the dimension of that object. Now the relation between them is cross product or vector product, if you remember in the first lectures. And the result of this is a vector. So the torque tau is a vector, and tau magnitude, if you remember from the cross product, I'm sorry, r, f, is it sine or cosine now? For the cross product, it is sine theta. So the magnitude of the torque is r, f, sine theta, theta between r and f. What is the unit of torque? It is newtons multiplied by meter multiplied by unit is for the sine. It is newtons meter, and the work is newtons meter. But they are different quantities. This is a force in general. This is not. It is not energy. The torque is not energy. I told you, x here, the object move this distance, but the object here does not move r. R, it is its dimension. Okay? I'll show you this. If I move this thing, this, then I put energy Fx, which is joules, newtons meter. But if I move it like this, I didn't move the R, I didn't change R. But X here will change from point to point, but R is the same. R is intrinsic property of that object, rotated object. Okay? So this is not energy. And the units of the torque still newtons meter. It will not be joule at the end. Is that clear? Any question about that online? Can you hear me online? I think yes, because there is. Yes, that's all. Thank you. Now, this is the torque. Any question about the torque? Previously, also, if you remember, we talk about the resultant force. For example, if we have this object and we have F2, F1, F3, then we have total force as a vector is equal to the summation of these forces. And so on. Also, we have a force now. This is a kind of force, but it is a rotational force. In our object, now, if we have more than one force, I'll keep it like this. Just the fixed point, the length R, and this is the direction of the R. And I will put now more than one force. For example, this is again F1. And this is for F1, this is R1 to this point. And the direction is the same. This is, for example, F2. And this is R2 to this point as magnitude. This is the length of R2. This is R3. And this is the length of R3. And so on. You can put any force. You can put a force like this. Or you can change the direction of this force. You just, when you change the direction, you will just manipulate the angle theta. Just like that. You need to find the angle between R and the force. Okay, what is the total torque? As a vector, if you like. We will talk about the vector property of the torque. It is simple. The first torque plus the second torque plus the third torque, and so on. We can use them like this. The total torque is equal to the first torque. It is R1 F1 sine theta 1 plus R2 F2 sine theta 2 and so on. R3 F3 sine theta 3. Just like that. We just add forces or rotational force or torques. Just we need to call them torques. In general, now, all of you, what is the difference between torque and moment? Okay, we will talk about moment, the moment of inertia. In general now, we will learn in our study new quantities in physics. Moment of inertia, momentum, kinetic energy, torque, and each one of them has its formula. The application and the solution of any problem will be the same. We just pick the numerical values and put them in the formulas. We just learn new quantities. Each day we learn one or two quantities in physics. Okay? Now, I will solve this example. Any question for now? We will talk about the moment. The moment of inertia, if you remember that, it is I. The torque is tau. The moment of inertia, it is the rotational effect of the mass, which is the mass multiplied by r squared in general. But the tau is the force multiplied by R by sine theta. This is a rotational mass or a rotational effect of the mass. This is a rotational effect of the force. And we have, for the moment of inertia, we have different shapes. If you remember, we have a cylinder, even it is a shell or a solid. We have a sphere, shell, and we have a stick. We have a flat sheet, and so on. We will solve an example. Use that moment of inertia with the torque. Okay, now we have example. We have a rotated object, yes, about the point O. And we have many forces. And each force has its angle and its distance from that point. We have, this is F1, this is F2, and this is F3. R direction is to this direction. This is the direction of R. At each point, we have a magnitude of R, length of R. So R1 has a length. The length of R1 is 1.2 meters. This is R2 here. The length of R2 is equal to 2 meters. The length of R3 is equal to 3 meters. Okay. This is just number. What about the angles? Now, if this is the point, this is an important point to locate the angle and to know where is this angle. For example, this is F1. This is the stick, the rotated stick. But R to that direction, this is R. Where's the angle? Is it theta 1? Or is it theta 2? Or is it theta 3? I have the formula R cross F. So I need to measure the angle from the first vector to the final vector counterclockwise. So I will start from R, ending with F. So which theta I need to use? I need first perpendicular. Wait. Perpendicular distance and stuff. Okay, I'll talk about this point. It is, you mean, their student here asked about the moment. The moment mean by that the force multiplied by the perpendicular. If the force act perpendicular to the distance, this angle will be 90 and it will be your moment. Now you will see that. Now, which angle we will use? We will start from R and reach F. So which angle is ours? Theta 3. Theta 2, this is minus R. We don't need it. Theta 1, it starts from F to R. We don't need it. If you tell me I will use this direction, no. Our angle will be measured counterclockwise. Okay? So our angle, theta 1 is this. And theta 1 is given, which is 200. Theta 1 is 200 degrees. What about theta 2 now? It is simple. Now, this is F2 and this is R. This is theta 2. It is given also. It is 100, I think. Theta 2 is 100 degrees. What about theta 3? This is R and this is F3. It is given. It is 90 degrees. Theta 3 is 90 degrees. Right? Yes. When we apply this, assume this is Y and this is X axis. And we have this angle. From before, we know that we have this X and Y. And this is F. This is theta. We have here Fx. This is F cosine theta. We use it in the dot product. We have here F sine theta, which is Fy. Now we use F sine theta in our relation. It comes from the cross product because we have R cross F is equal to R F sine theta. So now we use this direction of the force. Is this is now I'm asking, and for you, Emma, at Y direction, is the force the perpendicular or the tangential force? It is the perpendicular. This is F perpendicular. This is F tangential or parallel to our system. Now, in our solution, we use F sine theta. We use the perpendicular forces. What I mean by that? I will draw this part here again to make it more simple. This is the rotational point. This is the stick. This is the force, F1. This is theta. Now, apply your imagination. Now we have, this is the positive R. So this is the positive X. If this is the positive X, we need to go counterclockwise to find the positive Y. So our coordinate is rotated by the angle theta. This is the negative Y. This is the negative X. Okay? It is just rotated. It is our system, this one, but it is rotated. And the force, it is in the negative Y direction and the negative X direction. It is this one. This is F1 there. This is our system. Okay? When we apply the second and the third force, you will see it in a better way. Now, if I use F sine theta. So this is the perpendicular direction of the force or component of the force. This is F sine theta, which is the one I needed in my relation. And this is F cosine theta. The effect of this will be zero. You will see that. Now, my effective part of this force is just this one. Imagine that F1 is replaced by F1 sine theta. Then we will have the same effect because F1 cosine theta will not rotate the object. Where is the stick? This is the stick. I will try to rotate it. If I apply a parallel force like this, it will not rotate, right? This is F1 cosine theta. But if I apply another perpendicular force in this direction, like this, it will rotate it. If I apply a force with an angle like this one, this force has two components. One of them is parallel, it will not affect the rotation, and another one is perpendicular. It will rotate the object. So my moment, what you ask about it, Emma, it is the perpendicular effect of that force. Okay, which is F sine theta. I'm talking about F1 and theta 1. Okay? And the same for theta 2 and F2. F2 is downward like this. So it has a perpendicular. This is the perpendicular in this direction and tangential. This is F2, has this tangential part or component, and this is its perpendicular effective force. What about that one? The third force. The third force, it is normal. Its angle is 90. All of F3 is perpendicular to the to R. This is 90. F3 sine 90. Sine 90 is 1, so it will be equal to F3. But F3 cosine 90, it will be 0 because cosine 90 is 0. So the tangential component of F3 is 0 now. Now we will solve for tau 1, tau 2, and tau 3. Okay. Okay, tau 1 as a magnitude. I will not talk about the vector property of it. It is R1 F1 sine theta 1. It is equal to R1 is 1.2. F1, it is given F1 is 5. F2 is 10. Also, F3 is 10. Multiplied by 5, by, yes, 5. Multiplied by sine. This is sine 200, right? Sine 200 is negative value. You see that I draw the negative y direction upward. So this will be equal to minus 2.05. What is the units of the torque? It's in Newton because it is a force, and we have a radius. Give us the meter. What about torque 2 for the second force? It is equal to R2 F2 sine theta 2, which is equal to R2 is given also. It is 2 meters. The force is 10 multiplied by sine 100. I think this will be equal to the direction of, look, the direction of the first force is negative direction. It is clockwise direction. But for F2 and F3, it is counterclockwise. It will be positive torque. Right? F3, F1 will rotate, F1 will rotate the object clockwise. It is negative direction. But F2 and F3 counterclockwise, it will be positive. So this will be equal to 19.7 newtons per meter, not per meter, implied by meter, and tau 3 by the same way, it is R3, F3, sine 90. Now sine 90, this one 90 degrees. It will be equal to, will be more and more, it is 30 newtons meters. As you see, if we increase the radius, then the torque will be increased also. If we increase the force, the torque will be increased. If we increase sine theta, the torque will be increased. Any question about that? What is the total torque? We need to add them together. We have 2 of them positive and 1 is negative. The total work, the total torque. Now remove all stuff. The total force, we are talking about torque, not the total force. Okay, it's equal to tau 1 plus tau 2 plus tau 3. It will be, add them together, it will be 47.6 Newton meter. It is positive. Then the rotation or the acceleration of this object will be counterclockwise or positive. We will see now what is the acceleration. We know it. It is alpha, the angular acceleration. We deal with it from before. Okay, note that we talk about tau is a vector quantity because it is a cross product, and we will talk about its direction now. Its unit is Newton meter, and it is not a work. The positive torque is counterclockwise. The negative torque is clockwise. Okay. Another example. Yes, this is important. If you remember that from before, I asked you about x, f, cosine, theta. This is the work. I asked you from before, when we find that the work is equal to 0, it is, we have 3 cases, and there is a question in the exam. We have the first case when x, the motion, I am pushing now the wall, x is 0, then the work is 0. If we have 0 force, then the work is 0. If theta is equal to 90, 270, and so on, because theta is very big, then cosine theta is equal to 0. The same way we have for the wall, the torque. We have this example. The torque, when the torque is equal to 0, we need to put the relation. It is R, F, sine theta. We have 3 cases. The first one, when R equal to 0. The second one, when F equal to 0. The third one, when sine theta equal to 0. That means theta is equal to 0, or 180, or 360, and so on. These are the 3 cases. Let us apply them on our shape, this one, rotated. We have, this is the point of rotation, which is O. Okay. Any question? Line. Okay. Now, the first case, when R is equal to 0. If we, where is R equal to 0? This is the point of rotation. The distance R is away from it. This is R. When R is equal to 0, it is here. So if we apply a force here, 1,000 newtons. But R is equal to 0. If we apply a force like this, it will not affect the rotation at this point. Look at the door. There is no doors now in the range of the camera. If you apply any force at the center of rotation of that door here, the door is open and closed. If you apply any force at this point, it will not rotate the door. If this is this water source, if I apply, I'm rotating now. You are seeing me online. But if I apply any force at the center of rotation, it will not rotate. Okay? If I apply this force also, I need to be more strong. Okay? Now R equal to 0. What about the force? If the force is equal to 0, it's okay. If we have no forces, if we have the force equal to 0, then there is no rotation. There is no rotation here. If the angle now, be careful that we have a plane of rotation, and all of our system is in this plane. We are not talking about this plane. For example, we are rotating like this. I am not applying force like this in Z direction. Okay? It will not rotate the system. Our rotational forces is in XY plane. Okay, now the third one, sine theta. This is R as a vector, a direction. If my theta is equal to 0, means that my force is in this direction. The angle between them is 0. So if my force is like this, I'm just pulling, right? I'm not rotating. Or if I am pushing. If my force in this direction also, sine theta will be equal to 0. We don't have any force. It is the parallel force, what we discussed here. This is our rotational object. This is the force. It is 180 or 0. If I am pulling down. Okay? These are the three cases. The torque will be 0. Also, the torque is a vector. And this is an important point. Now, if we have this rotated stick about the origin, and we have, this is R, and this is F. You know that the rotation about O will be in this direction. This is omega, the rotation. We have velocity or acceleration now. Now I am asking, where is the direction? We have three directions, X, Y, Z. Where is the direction of the torque? Who can tell me? I'm applying this here. This is counterclockwise to me, from upward. Now, this is the force, and this is the radius. And the rotation in this direction. The direction of this plane is upward. The direction of the torque is upward at this point. it is perpendicular to the force and the radius. The direction of the torque is getting out from the board in this direction. This is the direction of the torque. If I ask you, and I didn't go deep with you with the cross product, this R cross F. At the beginning, we didn't talk a lot about this because there are some difficulties. One of the properties of this product, the result is a vector. For example, if I ask you about this area, you are seeing me here, about the table surface area. What is the direction of this area? It has a direction. If I ask you what is the area of this rectangle, you will tell me it's A multiplied by B. What is the direction of that area? If you told me it is A, I will tell you it's wrong. Or it is B, it is wrong. One direction between them, it is wrong. Because this is X, this is Y. And the direction of this surface is upward. You will see it. It is up. Its direction is upward. What is the direction of my face? It is forward. Now, what is the direction of my face? It is to the north. Okay? The direction of this area is upward. The direction of this area from downward, it is downward. So any surface you can imagine, its direction is perpendicular to it, outer, going out from. Any question about this point? Now we have the force and the radius. Both of them are in this surface, in this plane. From the properties of the cross product, the resultant vector is perpendicular to this surface. So, perpendicular to this surface, it is upward. If we take this is R as a vector, and this is the force. And this is the angle between them, theta. R cross F. It's a vector, and its direction out from the board. We need just to understand this point. I will not ask you a lot about it. What? This is, so R cross F, look, R cross F. It is going out from the board, and I will give it this shape. The point shape means out from the paper sheet plane or the board plane. But if I take the opposite direction, if I ask you F cross R, it will be in the opposite direction, and it will be going inside the board, and I will give it this shape. Okay, it is going inside the board. If I'll remove this. We are talking now about cross product. Because I am not talking about this point in the beginning lectures, I am talking again about it now. This is R, and this is F, and this is theta. R cross F, R cross F is going out, which is positive, for example. But F cross R, it is going inside the board, which is negative. So, look, if I put my right hand, I'm talking now about the right hand rule. If I put my right hand, my fingers, to the R direction and rotate them theta to the direction of F, this rotation gives me the this finger, is it the thumb or what? Thumb direction, outer from the board. It is the direction of the torque. But
if I take F cross R, I have to change the direction of my hand. It will be in this direction. So the direction to the torque will be inside, go inside the ball. Or I can use the left hand rule, not the right hand. I can use it, the left hand rule, from R to F to be inside. But keep that, you need to use the right hand rule. It is like this. Sorry. This is the R, F, the torque, yes. It is X, Y, Z. This is X, Y, Z. What? Y is with an angle. And we have this plane. The third vector is perpendicular to this plane. Even it is going out or going inside. So my force and R here, my torque is upward. Because it is positive and my rotation is counterclockwise. If my rotation is clockwise, then my torque downward. I'm talking now about the torque, which is a vector. Okay, if one of you asked me, okay, sir, we know more about omega. I'm not talking, I should talk about omega previously, but it is, I could put them all together. If this vector is rotating by omega, omega is a vector quantity and its direction is perpendicular to our surface again. If you remember that omega, I think it is R cross V. It is a cross product, which is R V sine theta. Okay, what about the acceleration, angular acceleration? We have alpha, it is angular acceleration. It is again has a direction. We see the object is rotating like this, but this rotation direction is perpendicular to it. I'm talking about this too much. Any question about this point? No. Okay. At each example or problem, we will talk about this point if it is difficult at that point. Okay. Now we will talk about the torque and the angular acceleration. We have a time for that. The torque and the angular acceleration. It is Newton's second law in rotation and motion, or rotational dynamics. The dynamics means there is a motion. That's squeeze. Now we are talking about section 10.2. If you remember that, the Newton's force is equal to M multiplied by A, right? As I told you from before, in physics we can put parentheses anywhere we want. We can multiply any quantity in our relation. If I multiply R and R, we don't talk about vectors now. It is just quantities. It is one R by R. It is the same, Newton's second law. But we know that R, F, what sine theta? Okay. Assume it a moment which is 90 degrees between the force and the radius. This is the torque, right? Equal to, we have M, we have the radius R, we have A. But from before, we know that V is equal to R omega. Alpha is equal to R A. when we just convert between the velocity and the angular velocity by multiplying by r, and angular acceleration and linear acceleration by multiplying by r. No, the opposite, I think. This is A, this is alpha. This is A. So A is equal to R alpha. Okay, this is another R, and this is alpha. R by R, it is R squared. Okay, put your parentheses here. Now we have alpha, we have R squared. R squared, if you remember, and I talk about this today, it is the rotational effect of the mass. It is the moment of inertia. For a point mass, this is a mass rotating about a point O with a radius R. And this is alpha. It is the angular acceleration, if there is any acceleration here. We have alpha at the acceleration. If you remember, we have a radial, which is v squared over r, or r omega squared. It is the centripetal acceleration. We will not use it today. We will use alpha, which is equal to the acceleration divided over r. This will be equal to the torque. We start by Newton's second law. F is equal to ma. It's simple. We just multiply by r and remove the linear acceleration and put r alpha, the angular acceleration. Then we have two r's multiplied by each other. This is r squared. R squared is the moment of inertia, I. Alpha is the acceleration, angularly. And tau is the force. The rotational effect of the force is equal to the mass. Rotational effect of the mass multiplied by the angular acceleration. It is Newton's second law again. Any question about that? It's simple, I think. Now, we need to solve an example. Just like that. Newton's second law and example. Remember that mr squared is the general formula for the moment of inertia. But I gave you a sheet with the, and you have that table for a cylinder, for a ball, for a disc. Well, each of them has its moment of inertia. Now, in our example, we have this tool. We use it, for example, to lift the water from a well, or using a rope. We have a cylinder. This is the axis of rotation. This is the radius. How much the radius for this? I think it is 0.1 meter. It is 10 centimeters. We have a rope rotated around it and going down. And there is a mass hang here. There is a tension force here, comes from the weight. This is weight, not omega and not work. The weight is equal to mg. M, it is given, it is 10 kilograms. G, it is 9.8. Now, my weight, the weight downward is 98 newtons. It is our force. So we have a force at this point acting downward. If you look at the cylinder from this direction, you will see this. This is R, and there is a force equal to 98 newtons. What is the torque? Okay. The torque is equal to I multiplied by alpha. The torque is equal to R multiplied by F, the first relation, multiplied by sine theta. But this is R. And this is F. Theta is 90. I start from the beginning with theta equal to 90 degrees. Theta is 90 here. So sine theta is equal to 1. I'll remove it. Okay. I will compute the top. Which relation I can use to find the torque? The first equation, I need to compute I. It is easy to be computed. But alpha, I don't know the acceleration. The angular acceleration for this cylinder. By the way, it is a solid cylinder. But the second relation, I can use it because R is given. It is 0.1. F is given 998. And sine theta is equal to 1. Okay, it is equal again to 9.8 Newton meters. This is the torque. I'll remove this because we have the relation written here. Okay, in my system, what I need can you compute? I can compute alpha, but I need to find I. I for a cylinder about its axis is equal to how much? Half. I think it is half. It is half mr squared. Half is half. The mass is given for the cylinder. It is 10 kilograms. No, it is 30 kilograms. Capital M. The radius, it is 0.1. I need to square it. This will be equal to, I'll put it there, 0.15 kilogram meter square. Kilogram meter square. The unit of the moment differential. Okay, I need to compute alpha now, which is the angular acceleration. Because the rotation of this cylinder, it will start rotating, okay? But its velocity, angular velocity, will increase by the time because there is a force. Now, from this relation, we have alpha is equal to the torque divided by I, right? Which is equal to, the torque is 9.8 divided over that number. It will be equal to 65.6 or 8. What is the unit of angular rotation? It is radian per square second. It is acceleration. Any question about these things? Any question online? Have 10 minutes. Any question? Okay. Yes. We have this fun experiment. If I have this, you can see it online. If we have, I'll share it. If it is simple. Yes. We have 2 homeworks now, I think. And there's no, these more about, if you don't need to, you can see, I will share it. Where is the share? Okay.
This is our lecture. And we have more about the torque and the acceleration. Okay. And what about this? If you look here, I think we apply and we saw example like this for a block and for a sphere in the previous lecture. When we find that the kinetic energy and the total energy is equal to 147 joules, and for if you remember, for a block, all of its kinetic energy is equal to 147. But for a sphere, it was 105 plus 42 for rotational kinetic energy, and this is for linear kinetic energy. If you remember that previously. This is a sphere, and this is a block. We have many shapes here. We have a hoop. The hoop, it is just like a ring. I need to remove this. We have a hoop, which is just like a ring. We have empty can, which is a cylindrical shell. We have a solid cylinder, just like the example what we saw. We have a sphere, we have a box. Which one of them has the most linear velocity if they start moving on this ramp from altitude h? You will see that all of the mechanical energy at first is equal to mgh. Assume it 147, just like the previous lecture. Can you see that online? All of the energy will be gained as kinetic energy for the box, and its velocity is equal to m2e over m. So the velocity will be maximum value for the box. So it will be the fastest one between the given bodies. Now, this energy will convert to kinetic energy, which is two parts. One of them, kinetic energy, linearly, plus kinetic energy, rotationally, radial. Right? The box, the block, its rotational kinetic energy is 0. So all of 147 are for the linear motion. For a sphere, its part for rotation, as we solved it from the previous lecture, it is 42. So it is kinetic. So kinetic energy here is 147. Kinetic energy for the sphere is 105. What is the next? The solid cylinder. This is a cylinder. Maybe its kinetic energy, for example, it will be 85, for example. We can compute it. For the next one, the empty can. This is, maybe it is 64. Its kinetic energy linearly. And the hoop, the last one. The hoop, maybe it is 50 joules. Its kinetic energy linearly. Okay, what is the kinetic energy rotationally here?
it will be 42. What is the kinetic energy for rotational here? It is 147 minus this. It will be for this kinetic energy rotationally. These numbers, it is just by assuming to understand the point. 2, 6. How much the rotational kinetic energy for the block? It is 0, right? Because there is no rotation. What is the rotational energy for this? Kinetic rotational for the spherical, the cylindrical shell. We need just 3, 14 ناقص 6 8. For the hoop, the kinetic energy rotationally for the hoop, that minus this, it will be 93, I think. So from this sheet, we have a relation between the kinetic energy linearly and the kinetic energy rotationally for each object. What is that relation? Add them together, it will give you the initial energy at this point. Each object has its abilities to gain more rotational motion. For example, the block, its ability to have a rotational motion is 0 because there is no rotation for it. The sphere, for example, can take rotational kinetic energy 42, as we see in the previous lecture. But we assume that the hoop can just take rotational motion more, 93 joules. From this, we can see that the rotation for each object different than the other. Because if we look at that, we can if we look at the mechanical energy, which is at first equal to mgh, it was 147 in our example, but it is equal to the kinetic energy linearly, which is half mv squared plus 1/2 I r squared for each rotated object. Assume that r for them all the same, but the difference between them is I for each of them is equal to something multiplied by m multiplied by r squared. Remember that for a sphere, I for a sphere is equal to 2/5 m r squared. For the cylinder, now it is half m r squared. For some objects, 1/12 m r squared. So we have a number multiplied by m r squared. So we have here m r squared always. And we have another number. This number relates to the shape. For the block, how much this number for the block? If I need to compute the moment of inertia for a block, how much? This number will be 0. So this total will be 0, the total kinetic energy rotationally for the block. So you can see this experiment online, and you can see that each object has its velocity. That is because the difference of these coefficients. If I, for each I, there is a different multiplication coefficient. coefficient like this one. But mr squared is the same between them all. For each of them, we have mr squared, mr squared, mr squared. But there is a different number here and here and here. The time, I think, I am done by this. There is no relation to solve, no example. We just need to understand this. Maybe in the future I have. By the way, we solved an example in the previous lecture on this. Okay, I will stop sharing. Any question online, offline? Okay, I'll stop the meeting. Thank you.